Okay, screen. Yep, today it works. So last time was a glitch somehow. The panel disappeared when in a share screen mode. I think it's a bug of Zoom. Okay, so we were discussing solution of a Schrodinger equation when you integrate in the direction in which the function is exponentially falling off. And I warn you that in such a situation, when you're following solution of the function, for which we know that it goes towards zero exponentially fast, the error of the integration will accumulate. And this is quite easy to understand. So if we first we need to understand how the equation or general differential equation is being solved. Namely, we know the value at one point, we estimate the derivative, and from this we calculate the value at the other point. Of course, in sophisticated solvers of differential equations, it's slightly more complicated, but nevertheless, the main idea is the same. You take the value at one point, you look at the derivative, you get the value on the other point. And when the next point is supposed to be way smaller than previous point, we clearly see that the only way that this can happen is if the previous value and the derivative times the step have to cancel. And if they cancel, that means that we have potentially a large numeric problem. So this explains us why we have lots of numeric problems when we are following the solution down the path where the function itself exponentially falls off. Okay, and just if you understand this, that it's very unstable to follow the solution in the direction in which it falls off very quickly, then you immediately understand that the right way is to follow in the opposite direction where the function exponentially grows, because capturing exponential growth is numerically very easy, while capturing exponential fall off is very hard, doesn't it? Exponential growth basically means that your derivative and the value have to sum up rather than decrease at each step. So that must be easy to follow. So therefore we said, well, we just invert our direction in which we go with integration, and we're going to get much better precision. So that's exactly what we're going to do here. So we're going to take still the linear mesh from some very small value. Again, it shouldn't be exactly zero, because when the value is exactly zero, we have 0 divided by 0. We should avoid that. Then we go to, let's say, r equal 20. Now we know that the Bohr radius is where electron is on average, where there is a large peak of electron cloud. So that the typical distance then is 1 in these units. So going to 20 is probably pretty large. So the function should fall off really pretty fast after this value. And we're going to take the 500 points. We are going to still check one S state, which is L is 0, energy is -1 Rydberg, and we're going to invert the mesh. So here, this RB is R minus minus 1. You remember the third entry in the such as taking slices means a step. And if you take step -1, it means you exactly reverse the mesh. Okay, so if we execute this, and then, for example, we check what is R, and we check what is RB, we will see that RB is exactly a reversed mesh from R. Okay, why? Because this -1 reverses the mesh. So now that we understand that, we then use, the only difference is that we use this reverse mesh in integrate O the int. We give this exactly the same Schrodinger derivative, but right now it's important to, who has a microphone that needs to turn off? It's important now here that we take the slightly different initial condition. Namely, the value in infinity is also 0, or it's a very, very exponentially small, so we can set it to 0. And then the derivative should be some small number. it actually doesn't matter which number we take, because this number depends. This number changes only the normalization of the function. So if this number is bigger, the function is need to be normalized, will be normalized with larger constant. If this function is smaller, this number is smaller, the function will appear with much smaller normalization. So since we are going to renormalize the function at the end of the day, it doesn't matter what we take for the initial condition. However, it's a good idea to take a small number, because otherwise potentially you can get an overflow, because these numbers tend to get exponentially larger, of course. So therefore, I'm going to take 10 to the minus 5, where numerics is still pretty good. We could go maybe to 10 to the minus 10, but not further, because if we start with 10 to the minus 16, then we know that the integration cannot even start, because this will immediately make numerical problems. So we take some small number, hopefully hope for the overflow is not going to occur. And then we do exactly the same thing that before, integrate to the int. And then when we are done, we take the 0th component, which is, or zero column, which corresponds to the solution, not to the derivative, but to the solution. And then we rotate it back, in the sense that we again inverse R in basically the in R space, we invert the entire array, so that now this UR is actually written in the mesh, in original mesh R, in which R is increasing. Okay, and then we can integrate this function with one of the available methods. Now, of course, we could create from this UR a spline, and then we could integrate spline with the regular numerical methods such as quad. You remember we look at the integrate quad function. Now, that's not advisable. Why? Because we have a solution for our problem on a discrete points. So discrete points are in horizontal direction. Discrete points correspond to R, and in vertical direction to UR. So in this case, we have to use integration routine, which can integrate function from samples, so-called integration from samples. And it's a good idea to check what are the best numerical methods for this case. And you can see that trapezoid rule is one, which is not advisable to use, because trapezoid rule has error bar of OH square, so the second order error. The Simpson rule has, I think, fourth order error, and it's pretty good. Now, Romberg method is slightly better than Simpson, but the trouble with Romberg method is that it requires exactly 2 to the power of n plus 1, where n is integer, sample points in linear mesh. Now we have 500 points in linear mesh which do not obey this. So we would need to make sure that we use 2 to the power of n plus 1 if you want to use Romberg. Now I wasn't careful at the beginning when I chose 500 points, so better to use Simpson method. Now the difference, for our purpose, the difference between Romberg and Simpson is not big enough to make any difference. But if you need slightly more precise method, when you have very, very smooth functions, then maybe you should look into Romberg method. But then you're limited with the number, with the how many points you can take to a particular set of points. Okay, so we're going to use Simpson method, and Simpson method requires data points, which in this case is u square. So we are integrating function u to the square from 0 to infinity, of course, and our mesh is R. And this will give us the number, which is the normalization constant, and then we divide this by square root of normalization constant. Okay, so we evaluate this. So now UR is given on our original mesh R, and it's normalized to unity, the way it's a Schrodinger equation, solution of the Schrodinger equation is supposed to be normalized. Okay, and now we can plot this. So I'm going to plot simple R UR, of course. So we're plotting the solution of Schrodinger equation. We also know the exact solution of the Schrodinger equation from, of course, from known analytic solution. And in this case, the analytic solution is actually 2r e to the minus r. So this 2 comes from proper normalization. Before we use r, but now we use 2r because we normalize function correctly. So it should go as 2r e to the minus r. And we are plotting these two together. And, well, look at this plot. They're exactly on top of each other. So maybe it's hard to see, but I can do label numerical. And this label here is exact. And then we can say legend loc is best, and we will see that the two exactly coincide with each other. Okay. Now another way to see this is, for example, using here with exact only dots, and the other one is going to be with lines. Now it's maybe easier to see that they're exactly on top of each other. Okay. Now, more interesting, of course, is we know that they coincide very well in infinity because that's what was our original condition. The question is how well they coincide at small r, close to 0. And so for this, we will zoom in. It's very small r from x from 0 to 0.01 and y from 0 to 0.02. We know that at small x, this goes roughly as 2 times r. So we go in y direction twice as much as in x direction. Now again, we can use, for example, here dots, so that it's easy to see that they, exactly match. So what's wrong with this? This is with lines and this is with dots. No. Now they're both with lines, and now is this one with dots. Yeah, I don't understand why I don't see it. So this with lines and this with dots. Let me do O. I see. The problem is that there is only one point here because our mesh is actually, our mesh is not so great. We have only one point at 0 and then one point pretty far away. We don't have many points, so therefore it looks strange. Yeah. So there is one point here and there is another point here. So they're exactly on the same line as the exact solution. So the point is that they exactly coincide. Okay. So the message is that integrating from infinity down to 0 works perfectly in the sense that the boundary condition for the exact energy -1 is exactly is very well satisfied both in infinity and 0. Okay, so integrating from infinity is stable. So even though the function vanishes also at 0, the point is that when it vanishes at 0, it vanishes slowly in the sense that it vanishes linearly, or even if it vanishes polynomially, quadratically, or cubically, that's still okay. The problem is when it vanishes exponentially, then it's very hard to follow numerically solution. Okay, so now we put all this knowledge together into a small routine, which we're going to use later on. So we're going to define this function solve Schrodinger. The input is energy, L and R. And then we're going to do exactly the same procedure as we've done here, but maybe I can condense this. So we are going to do this integrate O the int. We're going to use the Schrodinger derivative function, which was defined above. Then the initial condition is going to be value in infinity 0 and derivative in infinity is very, very small number. We're going to take negative derivative because we are integrating from, we are integrating down. Integrating down means negative derivative will give you a positive function. If we choose a positive derivative, it will give us a negative function. I mean, for the solution of Schrodinger equation, it doesn't matter whether the function is positive or negative, but we are kind of more used to positive functions. So therefore, we choose the negative derivative here. Then R is used only in one place, so we can definitely just inline here. We can remove R here. So we are turning around the mesh, and then we're getting the function, and then we actually don't need RB, the turnaround function. We can immediately take from this. Only the value, not the derivative, and we turn it around, and this will become UR. So now the function is becoming much shorter, and then finally we normalize this function and return the normalized function. So we could even condense this line more if need be, of course, because this can be done in line. So the nice thing about Python is that proper things are returned, and we can even get rid of one more line here if we wanted to. We don't need to write UR. We can immediately we can normalize this on the fly when we return. Okay, but so this is now condensed into one nice little function, and now we want to check the same solution for excited states of hydrogen. So does it work in general? Well, we're going to take L is 1 and N is 3. So in which the energy is 1 over n squared. You remember from the quantum mechanics course, the energy goes as 1 over n squared. So this would correspond to, if I'm not mistaken, 3p orbital, isn't it? Because 2p has an energy 1 over 2 square, but 3p has energy 1 over 3 square, isn't it? So 3p orbital. So does it work? Does this thing work? Well, first I want to take here the same mesh that we used before, yeah. So just this. Let me do this in another cell A, like this. Let us check that. Yeah, we need to plot R. Now we need to do plot RI, URI. Yeah, divided by RI. Actually, UI. Now this is linear mesh. Okay, so what I want to demonstrate here, and maybe this, but I want to demonstrate that there is a problem. Okay, so if we take the L is 0 and N is 1, this works nicely. But when we take L is 1 and N is 3, which is also supposed to be a solution of the hydrogen atom, we have a numeric problem. So what to do? So it seems we improved a little bit of stability for 1s orbital, but when we look at a 3p orbital, we still have a problem. Okay, but this time is not so bad, because well, it turns out that this is caused by somewhat imprecise numerics again, but it turns out that if we improve the mesh a little bit, so that we don't go, that we don't assume that the function vanishes at value R is 20, but if we go further to 100, then the error is much smaller. Okay, so what is this signal? Well, this is expected somehow, because the function at 20, 3p orbital is larger, isn't it? I mean, you can see it here in the plot that it goes to larger R. So 3p orbital is larger. So therefore, we need to go to much larger R before we assume that it's numerically 0. Okay. Now, the issue is, what if we go to, I don't know, 5f orbital? Do we then need to go to 1,000 and maybe 10,000 points? Well, it's not that bad. It turns out that even if we go to only to 20 or to 50, okay, there seems to be a numerical problem. But this numerical problem is not so bad. Namely, if we change the energy just a little bit, like 10 to the minus 6, we change the energy just a little bit, it turns out that this peak will get modified. So if we add here, let's say plus 10 to the minus 6, then we will see that this peak, you see, it's very different now. Okay, I change the energy just a tiny, tiny bit, and I see that in one case, the peak goes down, in other case, the peak goes up. Okay, so which means that there is an energy very close to the exact energy, which will satisfy the boundary condition. Okay, which means that, okay, I'm not going to get the bound state energies with more than 6 digits, but I will get a function which is correct. Okay, and unfortunately, if you want to get, of course, energy with more than 6 significant digits, well, then you need to pay the price that you need to go to a very high R, and you need to have a very, very nice mesh and so on. But in practice, you never need an exact energy. You need an energy within enough significant digits that some other error or some other approximation doesn't make it. There is always some other error, statistical error, systematic error, or something, and this should precision of your numeric should be bigger than other errors, and then you're fine. Okay, so the message then is, well, we need to go to slightly larger R if you want to gain the precision, and maybe more points. But there is a better workaround in this case. In this particular case, it's not always, but in this particular case, it works. So I want to show you this case, this example. Namely, we can take, instead of linear mesh, we can take logarithmic mesh. So right now we use linear mesh from 0 to 20, 500 points, but we can also take logarithmic mesh from 10 to the minus 6 to 10 to the power of 2, which is the same, well, which is basically up to 100. Yeah, this would correspond actually to this mesh. Okay, so we go, so 10 to the minus 6 to 2 in log space is the same as 10 to the minus 6 to 100. And in lin space, we use, linear space, we use 1,000 points. I want to demonstrate that if we use in logarithmic space only 100 points, we get basically identical solution. So to demonstrate this, I execute this, and you see the points are exactly on top of each other. Let's zoom it in. You see the points are exactly on top of each other. So in logarithmic mesh, we can reduce number of points for substantial factor, basically a factor of 10. And we get still pretty reasonable precision, the solution with the same quality. Namely, it still overshoots a little bit here. And the reason for this, as I explained before, is that if we want to improve this, we need to go even to a bigger X when we set value to 0. But the easier solution is just to slightly tune bound state energy. And with slightly tuning bound state energy, we can remove this peak. So now I don't know whether I need to add or remove. So yeah, this is too much actually, 10 to the minus 6. This is also too much. So we need to remove a little bit, but maybe 10 to the minus 7. No, it's also too much, 10 to the minus 8. So plus 10 to the minus 8. So anyway, we have to tune the energy just a little bit so that this peak will, this little problem at 0 will disappear. Okay. Now, of course, I tried to do this by hand, and I failed, but we have root finding routines for that, doesn't it? So this is what one of those routines that we discussed last time should become handy. Okay, so then the idea is to implement shooting algorithm. I just described shooting. Namely, we set the boundary condition in infinity to 0, derivative to be some constant, and then we're going to solve for the solution u of x down to 0, down to the other end, and evaluate the value at the other end, at 0, okay? So this is what this shooting routine should do. Let me walk you through. So first, we integrate our function Schrodinger derivative with exactly the same boundary condition as before, 10 to the minus 5, with R, which with mesh, which is turned around in R points, and then the resulting we take only the value of this function, not its derivative, and then we turn it around here because we want to eventually the solution to be defined on mesh R, not the inverse of R. Then we normalized, as we did before, the function, and then we want to evaluate this function u of R. We want to evaluate at R is equal to 0. Now, of course, one possibility to do that is just to take the first point, okay? That would be an approximation for the value u of R at equal to 0. But that's not as good as we can do. We can do better than that, okay? So we can do better than that. We can actually extrapolate the value down to 0 because the first point appears at 10 to the minus 6, okay? That's not exactly 0. So 0 is smaller, isn't it? So therefore, we can extrapolate the value down to 0. Now, how to do that? The best, you might ask yourself, why do we normalize this function first? Because if we extrapolate the function down to 0, why is normalization constant important for this function? Isn't it? We have a function, and it can be normalized to anything. It doesn't matter if we can extrapolate it to 0. We're going to get the same value. Well, it's a good idea to work with normalized functions because otherwise these functions can be very, very large sometimes. They can be of the order of 10 to the power of 100. And then these root finding routines get confused and they have too much numerical problems. So it is slightly more stable if you make sure that you normalize the function so that the function itself is of the order of unity, okay? All the routines kind of work better with numbers which are not too large or too small. Then the second trick that we are going to do here is we know something about such functions, okay? So of course, whenever you know something about your function that you're trying to obtain, use that knowledge. Now, what do we know about this function? Well, we know that the function goes roughly as a constant r to the power of l plus 1, okay? So therefore, it's a good idea to divide this function by r to the l, and then we know that the function is roughly linear. And then linear function you can extrapolate to 0 very, very precisely, okay? Even if you don't do this step here, if you don't divide by r to the power of l, you will still get a reasonable approximation. The problem is that if the function at small r is actually a quadratic function and you're using linear extrapolation, that is not going to be as precise as you can get, okay? So if you know from theory that the function is linear, then use linear extrapolation. If you know the function is quadratic, take quadratic extrapolation. Now, because I somehow didn't want to bother with quadratic extrapolation, we can use a trick, divide by proper function, r to the l in this case, and then we know that the resulting function is linear in R, okay? And once we know that it's linear, then we know how extrapolation works, isn't it? So we take a point in the very first point on the mesh. Well, this is the value at the very first point on the mesh, the value at the next point on the mesh, and then we estimate value at 0 by knowing by using the linear interpolation between these 2 points, doesn't it? So it's just extrapolating down to 0, linear extrapolation. And we return value at 0 now. So this is our linear extrapolation for the value at 0. Okay. Now we take the same mesh that we used before, logarithmic mesh from 10 to the minus 6 to 10 to the power of 2, like this, 500 points. And then we shoot with this R for the 2 cases that we had before, which is energy is -1 and L is 0. So this corresponds to 1s state. and we see that shooting indeed gives you some number which is pretty small, 10 to the minus 8. Now, if I increase this 2 to 2.2, I get number which is even smaller, 10 to the minus 9. Okay, so you see that by slightly tuning where in R space, yeah, this 3 is too much, basically. I have a problem then. It's unstable. So if you go to large enough R, you get better and better approximation for one s orbital. Now, the 3p orbital is still kind of problematic. You see that even if you use very, very large R, it still has issues. So there is some extra numerical little problem that occurs for this orbital. But as we will see later on, if you adjust energy just a little bit, then the bound state actually has correct R dependence. It will have just a little error on the energy. Okay, so yeah, this is not zero, unfortunately, but with just a little bit of tuning of energy, we will get it. Now, so now we understand how the shooting method works, but while we're not yet done, we need to implement the shooting method with the 2 steps missing. Namely, we need to use root finding routine. With using root finding routine, find the energy epsilon for which the value at 0 is equal to 0. This is the best bound state. And then continue with intrinsic energy until sufficient number of bound states is found. So that's what we want to implement now. Okay, so this little routine here, find bound states, is implementing exactly that. So we are gonna have some mesh, which I'm calling e-search. Now, how exactly this mesh looks like? Well, we're gonna play with it a little bit. In different parts of the code, we're gonna use slightly different mesh. But the first approximation, you need to know something about your solutions. So, for example, we know that they start roughly at, that it starts at -1 Rydberg, but even when you have interacting problem, then they might go down a little bit to maybe -2 Rydbergs, but not much more, because interaction doesn't completely change the spectrum. So you know that the starting of the energy is somewhere around -1 to -2, maybe with the order of 1. And then it gets very, very dense close to 0, because we know that at 0 energy, we start to get continuum, isn't it? When you start to have plane waves. But if you want to have a bound state, then energy has to be negative. And at the same time, we know that close to 0, there are lots of bound states, infinite of them, of course. And we don't need to resolve all of them, but we need to resolve enough of them that we can populate levels that we need for a particular atom. Because, well, atoms that exist in nature have finite number of electrons. So what we need to do is we need to take a mesh which is not too rough that it would miss a bound state, but doesn't need to be infinitely dense either, because all we need to make sure that is we resolve every bound state. We just need to have at least one point between 2 bound states. So if it turns out that this search mesh is too rough, then we might find 2 or 3 bound states within the same interval. And if that happens, then we're going to miss a bound state. So if the 2 solutions exist in the same interval, then there is going to be no sign change between the 2 points, and our root finding routine will fail. If there are 3 bound states within the interval, then the optimizing this routine for finding minimum, for finding zeros, will find 1 0 rather than 3, because it will not know that there are 3. It will find just one of them. So the mesh has to be dense, but it doesn't need to be terribly dense, because we roughly know the spectrum, how it looks like. Okay, so later on here we'll try to arrange some reasonable mesh here of how many points? 10, 20 maybe points. So maybe 20 points. It doesn't need to be so much, but they need to be somewhat reasonably distributed. And then we are going to ask here only for limited number of energy levels, which is called Nmax. So Nmax is maximum number of bound states that we require. We don't need hundreds of them. We just need maybe 5, 6. Yeah. And then, as I said, E-search is energy mesh, which brackets all bound states. Every sign change of the wave function at u is equal to 0 has to be on this mesh. Okay, so what do we do? Well, in this array EBNT, we're going to save. This will save all bound states. Okay, then we evaluate the function in the first point on the mesh, E-search. Okay, so this is for the first energy, u of r, u at r is equal to 0 for the first energy, which is actually E of 0, E-search of 0. So we do this, and then we go through all the mesh points, okay, for all the mesh points, and we evaluate the function on these points one after the other. Okay, so evaluate u of r is equal to 0 on all E-search points. Okay, now whenever we see the function changes sign, so basically previous energy and this energy lead to a different sign, which means that the product u0 times u1 is negative. It means there was a sign change. Whenever the sign change occurs, that signals that there is a bound state between these 2 points. Now, hopefully the mesh is dense enough that there are not 2 or 3, but we need to be careful about this. But as long as the sign change occurs, we are pretty confident that there is at least either 1 or 3 bound states in between. Now, there is one trick. Well, there is one problem here. Well, potentially could be one problem, that the sign change can occur when you have a 0 or when you have a pole. As we saw last time, when you have a function tangents, the sign change can occur also when you go through a pole. Doesn't need to be 0. But the good thing is that we know that for a solution of the Schrodinger equation, that doesn't occur. So there are no poles. Whenever there's a sign change, we have a 0 in between. So we are free of this potential problem. Okay, so once we see that there is a sign change, then we know that between this previous point, E-search I minus 1, and E-search I, there is one bound state. So therefore, we're going to use one of the methods for finding 0 and evaluate precisely what the energy of the bound state is. So here we can use any method that we looked last time. So I remember there was Tom's method. It was pretty good, high level. But right now I'm going to use a very primitive root finding routine, Brent Q, which is kind of general purpose, simple routine. I think it uses Newton's method. The important point is that I want to use one of those root finding routines that that brackets the 0. So in other words, it needs the interval a and b, and then it finds the 0 in this interval. So we require that the 0 is exactly within this interval from a to b, not that we give a good approximation for the energy, because then this might find some other energy nearby. We don't want that. We want to give it an interval, and then we want the shooting method to find 0 within this interval. So Brent Q is one of the methods which takes as an input the both value of the interval a and b for the brackets. And then one important point which it took me some time to realize is that we need to use very, very high tolerance, very, very small tolerance, actually, the error bar, to determine the zero. We need to set this to very, very small number, 10 to the minus 16. You cannot force this to go much lower than that, because as we remember from before, double numbers don't have precision more than 10 to the minus 16. So you cannot make this number way smaller, but nevertheless, we use here extremely high precision with which we force the root finding routine to find the root, to find the zero. Why? Because it turns out that if we don't set this tolerance to be so low, then the bound states are not going to be precise enough. Now, what's the problem? Well, look, the problem is that the bound state might be wrong for 10 to the minus 15, 10 to the minus 10, let's say, okay? So for our purposes, energy 10 to the minus 5 wrong might be okay. I will not complain about total energy, but then when you try to plot the function, you will see exactly the problem we had before, which is that the function itself at 0 will explode, okay? So if you don't set this tolerance to be very, very, very good, then you will have the problem that we had before, namely the function, instead of going nicely to 0 at 0, will explode eventually, okay? So therefore, this tolerance actually helps. Make tolerance very, very small. Then you evaluate this function extremely precisely, and then you use this extremely precise energy determined numerically, not analytically, but numerically, that will give you perfect wave function that goes to 0 at 0, as it should, okay? So that's the trick. You need to use this tolerance to be extremely small. That's something that is kind of obvious once you hear it, but it's non-trivial to figure out when you see this numerical problem at 0. Okay, so we're going to find the bound states, numeric bound states. Then we're going to save this bound state. So both L and bound state. Why? Because we want to know later on when we sort the bound states, we want to know which L does this bound states correspond to. So we want to know the L quantum number once we fill them in, and then we're going to say if we have already enough bound states, we found as many as the user needs, then we can break, which means break. You can finish the loop. So we go out and then return the bound states. But if the number of bound states is not enough yet, then well, we increase n, which means that we now know that we have one more bound state. We can print it out. We're going to print this bound state, and also we know in this case the exact energy for the bound state for hydrogen atom, of course, not in general. Of hydrogen atom we know, so we're going to print also what is the exact bound state. And then we need to set U0 is U1 because we're inside the loop where we are increasing this energy E search. So we are jumping from E search of 0, E search of 1, E search of 2, E search of 3, and so on. So we are looping through the energy on this mesh, and we are evaluating. We are bracketing the 0. Once we see that the 0 has occurred between the 2 points, then we find the bound state very, very precisely with this root finding routine print Q. Okay, so I'm executing this, and now everything is ready for finding all bound states of the hydrogen atom. Okay, so for this we're gonna start with we're gonna use R in logarithmic mesh like before, from -6 to 2.2, let's say 500 points in logarithmic mesh. Now this mesh for searching bound states, we're going to use again some knowledge from exact solution. We know that exact solution has this 1 over n square dependence for energies. Now, of course, we know here exact energies, but we're not going to use this information. We're just going to, because when we have interacting problem, the energies are going to be different. but qualitatively, they're still going to be similar in the sense that the spectrum will get slightly modified, but it's not going to be completely different. So we can use this knowledge that that the spectrum has roughly 1 over n dependence, 1 over n squared dependence. So we're going to use, we're going to go from 1 to 20 with the small step 0.2. So we're going to make 0.2 step, and then we're going to square that, isn't it? And this is going to be our mesh. So to demonstrate what exactly that means, search. So we're going to start with minus 0.2, then minus 0.08, and so on. And you see this gets denser and denser close to 0. Okay, so that's the mesh on which we're going to evaluate function. Now, this mesh should not miss any bound state. I mean, eventually close to 0, it will start missing them. But that's not our problem because we don't need so many bound states. We need maybe, well, in this case, 7. We're going to say up to 7. So this is more than enough for any atom in the universe. Okay, so of course, if this is not good enough, then we can, of course, reduce the step, maybe, if need be. But this is more than good enough. Okay, so then we're going to say that the maximum number of bound states we need is 7. And then we're gonna find the bound states. Well, here we're gonna loop over all L quantum number, isn't that L quantum number? Because we need to find L is equal to 0 bound states, L is equal to 1 bound state, L is equal to 2 bound states, and so on and so forth. And then this find bound states is our routine that we just coded here, and this gives us a list of L and energy. L and energy, okay? And so now when we go through this, when we call this for L is equal to 0, it will give us a list for L is equal to 0. Then we will go to L is equal to 1, and it needs to give us a list for L is equal to 1. And then L is 2, L is 3, L is 4, and so on. And we are going to go all the way up to L is equal to 6. So L, of course, being orbital quantum number. So we're going to go with orbital quantum number up to L is 6, and every time we're going to evaluate 7 minus L 7 minus L bound states. Why? Because, well, we know that let's say 4 S state has much higher energy than 1 S state, doesn't it? So therefore we know that the energies that we don't need so many energies when quantum number L is large, isn't it? Because they start with very high energy already. So yeah, so we execute this loop, and so we're going to get bound state. So first we do it for L is equal to 0. We get the bound state at energy minus 1. The exact energy is exactly minus 1, but our approximation is minus 1, and then 1, 2, 3, 4, 5, 6, 7 zeros. So our error bar is 10 to the minus 8. Okay, 10 to the minus 8, pretty decent total energy. Okay, now again, this error bar that we get is essential to get it, because if we didn't, then our wave function, when we look at it very, very closely, it's not going to go exactly to 0. Okay, so we need to use this approximate energy to make sure the wave function goes to 0. And this is not a huge problem, because total energy up to this precision is good enough for us. Now, if you want to get better precision, then probably 1,000 points might help. So a little bit more points, well, in this case, it doesn't. Then I guess slightly different mesh would maybe help. But it's interesting. 1,000 points doesn't improve, which means that it's not a problem number of points. Might be the problem of where we set it to 0. So maybe we need to go to a different cutoff. But with this error, we can survive, doesn't it? For us is enough. We're going to do later on numeral method, and we will improve this precision a little bit further with a different type of solver. Okay, so then when we look at the 2S state, so again, we see that the precision is pretty high. So I guess the error bar is even smaller. So this would be 10 to the minus 9, I guess. Then when we go to the 3s state, the error bar is even smaller. So this is less than what we print here, less than 10 to the minus 10. So, and so on and so forth. So actually precision of all these bound states, you see it's very, very high for S state. Then we go to the P state. Yeah, these are P, so L is 1. So this is 2, no, S, no, this is 1s, 2s, 3s, 4s, 5s, 6s, 7s. Now we have 2p, 3p, 4p, 6p, 7p, 8p, I guess. And then we have the D, which is 3D, 4D, 5D, and so on and so forth. Okay, so these bound states are more than enough for any atom in the universe, doesn't it? Because no atom in the universe has L is 5. These energies are not relevant. Okay, so we have more than enough bound states, and we see that at least for hydrogen atom, they are very precise enough for our purpose. And now, what do we need to do to solve the problem of general atom, hydrogenic-like atom? Well, the ultimate goal is to calculate charge density, because when we start adding interactions, we're going to need the charge density, or basically the wave function. If we know the wave function, we know everything. But right now, we're going to just use the charge density. So rho is a function of R, in order to improve, well, to calculate, for example, Hartree potential as a function of R, or to calculate exchange correlation potential. So how do we calculate the charge density? Well, charge density is basically proportional to our wave function square, doesn't it? So in order to do that, we need to first sort those bound states in energy, and then we need to populate enough of them that will accommodate all the charge that we have. So if the user decides that he wants to simulate an atom with 20 electrons, then we need to find the lowest few bound states that can accommodate this charge, doesn't it? So in order to do that, first thing to do is to sort the energies, the bound state energies according to their energy. Okay, so naively you would say, well, that's a really simple problem. I have these B and D's. Oops, I have B and D's, isn't it? And so this is a list. The first index is L. The second index is energy. So what's the problem? I can just I can do sorted, and then I can say key is equal to just a second. How does it work? Key is equal to lambda x of 0. Yeah. Okay. So as far as I remember, we discussed the sorting algorithm, isn't it? Sorting algorithm in Python 3, it needs so-called key function. Okay. So in Python 2, we were able to give something which is called compare, CMP, and CMP would use two arguments. It would compare two elements, x and y. So it would need two input variables, x and y, and would compare x and y. But Python 3 does not allow that. Python 3 allows only function which uses single element, and he needs to translate into a variable that can be sorted. Okay, so in this case, it's easy. We just take the variable is just the whoops, I sorted this wrongly. X of 1. My God. In this case, it's easy because all we need to take is the energy. So bound states have the first component is S, the second component is energy. So all we need to do is we need to take the first component, the component 1, which is the second component. which is energy, and then we sorted these bound states according to their energy. Okay, so that looks fine, the first approximation. So we have all these energies now, and we just populate them. Well, but if you look at it closely, this is not so great. We have one S state first, then we have 1s and 2p. This is fine, but then when you go to this three states, 3s, 3p, 3d, we get 3d first, then we get 3s, and then we get 3p. And then we go to four states, we get 4s first, but then we get 4d, and then 4p, and then 4f. Okay, so why that happened? Well, the issue here is that, of course, a hydrogen atom has accidental degeneracies, isn't it? So the energy 2s and 2p accidentally degenerate, and 3s and 3p and 3d accidentally degenerate, and so on. So when we turn on the interaction, this degeneracy will be removed. Okay, and then life is, in some sense, is going to be simpler when it comes to this sorting problem. But right now, because of accidental degeneracy and because we didn't calculate energies to high enough precision, the S and P and D state might be reversed sometimes. And that's definitely something we don't want. We want to first populate S level and then P and then D, okay? Because we know that when we turn on interaction, the S state will be lower than P and P will be lower than D. Well, there is some little inversion in periodic table. The 3D go lower than 4S, but let's say that we neglect this for now. We want to have S first, then P, and then D. Okay, that's what normally occurs. Now, how do we do that? How do we reorder, for example, these three energies in proper order, in the sense that S is going to come first, then P, and then D? Any idea? Any idea? Anybody? Can you help me? Well, in Python 2, it was easy. You have the CMP comparing. You could compare two entries, and then you could say, well, if it turns out that the total energies are within certain error bar, let's say total energy differ for less than 10 to the minus 6, then look at the L quantum number, okay? And take the one which has smaller L first, okay? So that would be one algorithm. So you look at the energy first, and you say, well, if energies are substantially different, then sort according to energy. But if energies are very, very close by, like less than 10 to the minus 3, then look at the orbital quantum number and take the one with the smaller orbital quantum number. Now, unfortunately, in Python 3, they do not allow any more compare function. So they want you to construct a number, presumably floating point number, from your element. Now, this is what I came up with. So if we take energy first, x of 1, and then we add L quantum number, L is 0, L is 1, L is 2, but we divide this L with roughly the precision with which we know the energy, then the sorting will be correct. Okay, so once more, if I know that the total energies differ for less than 10 to the minus 3, okay, then I can add to the energy the L quantum number and divide by some large number for which I know that the energies have precision on that digit. And then this will return me a floating point number for each entry. And if I sort these entries, then the total energies will be sorted the way I want. Okay, it's understandable. Okay, so what I'm going to do this is I'm going to sort them, and then I demonstrate that actually this does work the way I want it. So you see, we have 2s and 2p first. This was correct before as well, but this now it's inverted. So from 3s, 3p, 3d, it's correct. Okay, why? Because the total energies are definitely precise to 10 to the minus 3. And then if the degeneracy, well, of course, the important point is that the difference between these total energies here is supposed to differ for more than 10 to the minus 3. And there are cases where this might not work. Yeah, thanks God it didn't occur here, but it might. So maybe 10 to the minus 4 is better bet in general. So of course, with this trick here, we don't want to reverse the energies here. Okay, so we want to be a bit careful. This number has to be small enough that it only corrects the accidental degeneracies of the states. Okay, and since the splitting between the energies is still substantial, I guess it's still bigger than 10 to the minus 3. This works pretty well. Okay, so this is now sorted. So our bound states are sorted according to energy, and now you want to put together enough states, fill enough states so that you get charge density for an atom. Okay, so here I wanted you to do the homework. So in the online version of this code, I did not put the very last part of the code because I hope that you can finish it yourself and then submit the homework. If I put online the finished homework, then you're going to ask me, what should I do? Isn't it? I want you to do something. So I want you to finish this last piece with which you calculate charge density. Well, maybe this part is already there. It's later on. We're gonna. I think this is still online. Yeah, later on in numeral algorithm, it's not. Okay, so let's say that we have something like nickel atom. Z is 28. Then we want to populate the charge density rho, which is going to be an array of the length of R. So basically, the array is going to be as long as the mesh in real space in R, distance from the nucleus. So this rho is going to contain the charge density. Okay, so how do we calculate the charge density? Well, we will go over all bound states. We're going to take out the L for this particular bound state and energy in this particular bound state. Here, it's important that we go through these bound states in the ordered way. So these bound states are already ordered. So we here try to make sure that B and D contains the ordered bound states. And then all we need to do is to populate them with correct degeneracy. That's it. Okay. Now, we solve the Schrodinger equation on that charge density. So the source Schroedinger is something that we defined up there. You remember at the time when we figure out how to solve the Schrodinger equation, I said, let's write this into a function which can solve Schrodinger equation for an arbitrary energy L and R. We have this routine, so we can now just solve Schrodinger in our energy L and R. And the nice thing is that we're going to solve the Schrodinger with exactly the same routine with which we found the bound states, which means that this function U of R will not have a numerical problem that we saw before. They will be compensated, okay? Because we calculated energy with the same method with which we calculate the function. Okay, so this will give us now the entire bound state, the R dependence of the bound state. Of course, we've done this many, many times when we were shooting, but we didn't save the function. So when we're shooting, we throw away the information. Once we found the energy, we throw it away, and now we need to recompute it once more. But it's cheap, so it's really not a problem to do it once more. We've done it probably 100 times before to get the bound state. Now we do it one more time so that we know how the function u of r looks like. Once we know that, all we need to do is we need to add to the rho is this charge density square times some factor. Now this factor normally would be just degeneracy, which is 2 times 2 plus 1, isn't it? This is the degeneracy of each level. So as we discussed last time, this 2 comes from spin degeneracy, and 2L plus 1 comes from orbital degeneracy, because each orbital is degenerate for 2 times orbital quantum number plus 1. This is the orbital degeneracy that we heard in quantum mechanics. So for each function, we can add up to this dn times this orbital, up to dn times, isn't it? Up to. But we also know that the last level might be partially occupied. So not all the levels for each atom are fully occupied. Okay, the last level might be partially occupied. So how do we take this into account? Well, one way is to think of it as a Fermi function problem. So we know Fermi function gives you partial occupation of the levels which are close to the Fermi level. Of course, Fermi function is important concept in case when you have a continuum of energy levels, such as in solids. But it can be used here as a concept in finite systems as well, even though in this case we have discrete levels. But it's useful to think of it as a partial occupation, is like Fermi function, isn't it? Partial occupation. So what is the partial occupation for this orbital? Well, if this particular degeneracy of the orbital is less when we add all the orbitals up to now. So n counts occupation of all the orbitals up to now, and then we add this particular orbital to all the orbitals up to now. And if this is still less than z, then Fermi function is 1, which means that you take the entire degeneracy of the orbital and add to the current charge density. So basically, we're going to add dn times Fermi function, isn't it, times u square to the charge density. Okay, so Fermi function is 1 when we can accept or add all the charge density that corresponds to this orbital. However, if n plus dn is not any more less than z, but n plus dn exceeds the charge density or the charge that we need on the atom, then we take only partial occupation. And how much? Well, z minus n divided by dn. Okay, so because z minus n is less than dn, okay, z is the charge of the entire atom, n is the charge that is already accumulated from previous orbitals. So z minus n is the charge that I need to add to this last orbital that I'm occupying, isn't it? So z minus n is the charge that I need to put in the last orbital. And then dn is the charge that I can put, maximum charge that I can put in the last orbital. And the ratio of the two is exactly like a Fermi function. It's the partial occupation of this last orbital. So then Fermi times dn is the real occupation of the last of any orbital, even the last one. And then here for convenience, I'm going to divide u square by 4 pi r square. Now, why do I do that? Well, because I want to store the charge density per solid angle per radius. This is just my choice. I could store just u square, and then when I plot, I might either multiply or not multiply with 4 pi r squared. That's not so important. Now, the reason that I'm doing this is because later on, when we solve the atom with more advanced methods, when we take in the interaction, then we are going to need charge density per solid angle per radius, which is per point, on each point in space in order to calculate, for example, Hartree potential, or if we are going to want to calculate exchange correlation potential or Hartree potential. In both cases, what enters is basically d rho over d omega dr, which is d rho, which is the charge density per point. Okay, so you can think of it as d to the 3 rho over dx dy dz. So what's the charge density per point in 3D space? Okay, so once more, this d rho is actually the contribution from this orbital to the charge density in each point in space. And then we add this contribution to rho, which whatever has been already accumulated, we add this dn, or this degeneracy, to n. This has already been accumulated. We could add here dn times firm, of course, because that's exactly how much we're going to add in the step. But that's okay. We can use dn only because that's actually safer, because in the last orbital, this n will now exceed z. And that's good, because then here, if we check when n is equal to z, bigger than z, we break. If we multiply this with firm, that might not work sometimes, because this n plus dn might accidentally be just tiny bit less than z, and then we're not going to break, and we're going to accumulate too much stuff. So this is actually safer to add the entire d, and then we know that once we add a charge of the last orbital, we exceeded z. We definitely exceeded z, and then we break. Okay, now we execute this for n is 28, and we see we used 1s orbital, we used 2s orbital, we used 2p orbital, we used 3s, 3p, and 3d. And we see here accumulation of n. The first orbit takes 2, the second orbital takes 2, and the entire n is 4. The next orbital takes 6, and the entire occupation is 10, and so on and so forth. Okay, so this works. And these are the energies. Now, if we choose something bigger, let's say 28, 29, then we see that the last orbital, which is going to be now, what is it, 4s? The last orbital has Fermi function half, and occupation then becomes 30. Okay, so this works. And again, 30, 31, 32, for example, might be interesting, because in this case, Fermi function is 1/3. Okay, because we are putting 2 electrons in a p orbital, which has degeneracy 6. So n becomes 36, but in reality is only 32, because we added this n plus dn here. We added entire n. So the degeneracy is correctly calculated to be 1/3. Now, of course, we can now plot this charge density. Okay, we use from pilot import star and so on, but basically we're just plotting r rho, and now we multiply rho with 4 pi r squared. So basically now it turns out that for plotting, it's better to plot the charge density not per point in space, but per r in space. Okay, so multiply with r squared. 4 pi is not so important, but r squared is important, because otherwise the charge density at small r is enormous. Okay, charge density is enormous at small r, but it's integrally small. So therefore, this quantity is better to plot. Well, we see that it has contributions from various orbitals. So this first bump here is from the s orbital, from the 1s orbital. Then the second bump is probably from the 2s and 2p. The next one is probably from 3s, 3p, 3d. And there is even one further out, which I think is from 4s. Now, of course, you could also plot each contribution separately if you wanted to, and you could see how different orbitals are kind of contributing to this relatively complicated atomic charge distribution. Okay, so this demonstrates how to solve hydrogenic-like atom for generic Z. Okay, 28, for example, is for nickel. Let me go back. Nickel slightly easier. And this is something that's going to be for the homework. Now, but we're going to improve this code a little bit, and then I'm going to give you homework. Namely, later on in the second part of the homework, the second part of the lecture, we're going to solve this problem in so-called local density approximation. So we're going to add interactions into the atom, and we're going to actually solve the atom with kind of state-of-the-art approximation, local density approximation. Now, it turns out that there are these approximations are somewhat non-trivial to code, and therefore there is a reference data available at NIST. I wanted to show you that. So if you go to the NIST website, I provided the link in the next exercise. There is a NIST website which basically tabulates for each element. Yeah, I'm actually interested in oxygen here. For each element, it tabulates this solution. So it tabulates total energy, it tabulates kinetic energy, Coulomb energy, exchange correlation energy, and the energy of the bound states. You see energy of 1s state, energy of 2s state, energy of 2p state, okay, for any element in periodic table. Now, of course, our current approximation is completely neglecting interaction, and that type of thing, of course, can be done analytically, so it's not tabulated here. But when we add so-called local density approximation correction, then we can actually rely on this database at NIST, so we know when our code is working, because we should get exactly this numbers, okay? So if our code is working, we should get exactly the numbers tabulated in NIST, at NIST. Well, of course, our code is not going to be infinitely precise. So these values here at NIST are state-of-the-art in the sense that they push precision as much as they can, and I'm sure that their code is pretty slow. We are not going to try to get all the digits, but we're going to get pretty significant number of digits, maybe 2 digits less than that tabulated here, but sufficient number of digits that it's going to come pretty close to the solution. But this is going to be next time. Now, before we go to that, we want to improve our algorithm a little bit so that we can then more efficiently iterate this. The problem is that the local density approximation relies on the charge density. So now we did the entire solving the Schrodinger equation and finding the bound states and all the stuff. So eventually we managed to get charge density. Now it turns out that once we know the charge density, only then we can calculate what's the interaction. So only then we can get the potential which is needed to calculate interaction, such as Hartree potential or exchange correlation potential. And then we need to go back and solve everything again. And so this would require iterations. And iterations are slightly more expensive. They're doable, but slightly more expensive. So before we jump to that, we want to improve the algorithm a little bit. And there are, of course, lots of improvements we could do. But one of them, which is very simple, and I want to show you that, is so-called numeral algorithm. So instead of solving the Schrodinger equation with the general purpose O the int algorithm that we've used up to now, we can make this much faster, okay, with very small effort. And the algorithm is numeral algorithm because it turns out that if your function has a particular form, in this case, has a form like this. So second order, we are solving a function in which second order derivative is given in terms of the function itself or some other constant function, then the solution is much simpler to obtain. Once more, this numeral algorithm works for the functions which are second order differential equations in which the first order term does not appear. Okay, so generically, when you have a second order differential equation, you also have a first order term, the first derivative. And in this case, of course, we cannot use numeral algorithm. But when the second order derivative is given in terms of function itself, x of t, and an arbitrary extra function f of t and an arbitrary extra function u of t. So f of t and u of t are constant functions, while x of t is the dependent function. So if the function has the differential equation has this form, then we can use a simpler and very efficient algorithm, which is called numeral algorithm. Okay, so again, the importance here is that we don't have first order derivative appearing in the equation. Now we're going to see in a minute why this is so important, or why it's then life is much easier than normally. So this is because of the special structure of this differential equation. The fourth order error cancels and leads to sixth order algorithm using second order integration scheme. So it's way simpler than, for example, using Runge-Kutta. So how do we demonstrate that? Well, it's very, very easy. So therefore, I'm going to do it here in a few lines. To do Runge-Kutta takes much more time than this. But this I can do here without much problem. So what do we do? Well, x of t is our function, dependent function that we're looking for. Okay. If we expand this x of t to some high power and take into account the time Rolle's symmetry of the equation, all odd terms cancel. So what does it mean times reversal of this function? Well, if we make a step forward or step backward, there is no first order derivative here, so the function shouldn't change. So the function should have a perfect symmetry between h and minus h. Namely, let me explain this more precisely. So we are doing Taylor expansion here for x when we go from point which we call 0. 0 can be chosen arbitrary. So we start at point 0 and then we expand around 0 for the value of the function at small distance h away. So what is x of h if we know x of 0? Well, that's the Taylor expansion. X of h, provided we know x of 0 and the derivative at 0 and the second derivative of 0 and third derivative of 0, fourth derivative of 0, fifth derivative of 0 and so on, then we can write what x of h, what is a good approximation for x of h. If we go to infinity, then we get an exact solution. But if we truncate somewhere, then we have expansion, then we have expression for x of h up to, let's say, sixth order error. Now, we can not only that we can go with a step forward into plus direction, we can also do the step backward in the minus direction. That's also a problem. This is also can be done. And then what happens? Well, h becomes minus h in this term, in the odd term, in all odd terms, yes. H changes sign, therefore odd terms change sign. And the derivative, of course, at 0 is still derivative at 0 in both equations. Okay, so up to now, haven't done any approximation or anything, just expanding x for a small step ahead and small step backward in an arbitrary point 0. Now we sum these two equations together. Okay, we just sum them. And then we get the equation that x of h plus x of minus h plus is equal to 2x of 0. And then we see that all these odd terms cancel out because there is a sign change. So we sum the two together and then we get only h squared times the second derivative at 0 plus 2 divided by 4 factorial h to the 4 fourth order derivative plus something that has to do with h to the power of 6, which we neglected here. Okay. Now here, what I'm getting is basically second derivative, x double prime of 0, doesn't it? X double prime of 0. Now, however, I have because I'm solving the Schroedinger equation, I know that x double prime of 0 is given by f of 0, x of 0, u of 0, because that's what the Schrodinger equation tells us. okay, or this particular equation tells us. So I can insert this second derivative in here, and I have a nice expression for the the relation between x of h, x of minus h, and x of 0. And this has only fourth order error. But we're going to even improve this. We're going to get to the sixth order error next time. Now, the unfortunate problem is that the time is already 6:26, and therefore I should stop here. Is there any question, any urgent question tonight?
Professor?
Yes?
When you've been talking about homework, I'm a little paranoid now. There's only been the one homework so far that you've collected, correct?
That's correct.
Okay, and do you have any idea when this is going to be assigned or due?
Well, when we got there, so basically, as far as I remember, there is, yeah, so here, put it all together. So when I wrote here, put it all together, on the online version, which you probably downloaded today, it says put it all together, homework. Okay, so this part here is left for the homework. So when are we going to get there? Well, next time, I'm sure, because it's only a few lines down. What is going to be next time? Wednesday. Oh, so then you have an entire spring break. Okay, so it's easy.
I was hoping to hear.
Yeah, shouldn't be a problem. Yeah, so unfortunately, not many homeworks this time. Should you give me more? Okay, any other question? No, it was all clear? Easy? Easy. Let me stop recording.